there is no such thing as now in the universe. Every star you see is already history. We measure life in meters and minutes, but beyond Earth, those units collapse. The universe is too vast, too old, too slow to be measured that way. Out there, distance is written in time. Light has to travel, and while it does, the present disappears. The farther we look, the deeper into the past we fall. This is why the universe isn't mapped in kilometers, but in light years. Not distance, delay. A light year isn't a prediction. It's simply how far light moves in 1 year. Tonight, we're fixing that and rebuilding the meaning of a light year from the ground up. Most people meet the word light year already carrying a quiet confidence that they know what it means. It sounds familiar enough. A year is time. Light is brightness. So the mind stitches them together into something like a calendar for space. A light year becomes a poetic way to say a very long time. Stories use it that way. Conversations use it that way. And slowly the mistake settles in so deeply that it stops feeling like a mistake at all. Yet that small slip in intuition bends everything that follows. If a light year is imagined as time, then when someone says this galaxy is 2 million light years away, the sentence quietly mutates into this galaxy is 2 million years in the future, or 2 million years from us. The distance becomes a date, the location becomes a when, and the true structure of the universe, which is built on distances so large they must be expressed in the travel time of light, is blurred by language before it even reaches consciousness. The confusion is not foolish, it is an honest consequence of how human beings have learned to survive. For almost all of our history, distance and duration have been the same thing. How far away is the river, as far as your legs must carry you? How distant is the next village, as many days as the trek demands? In this ancestral world, meters do not matter, hours do. The nervous system quietly fuses how far and how long, because, for walking primates, they might as well be identical. That fusion works perfectly on Earth and fails almost completely in the cosmos. Light does not walk. It does not rest. It does not get tired, thirsty, or lost. It moves at a fixed, violent speed that makes our idea of fast look motionless. Because that speed is constant, time and distance can be translated into each other with perfect reliability. A second of travel at the speed of light corresponds to about 300,000 kilometers. A minute, 60 times more. A year, unimaginably more. When physicists and astronomers speak of a light year, they are not telling you how long you must wait for something to happen. They are telling you how far light can go while a planet orbits its star once. You can imagine a single photon, a particle of light, being released into empty space and allowed to travel without interruption. It races forward for one entire year on some distant clock. The straight line it traces in that time is 1 light year. The year here is not about the calendar you hang on a wall. It is a way of turning the speed of light into a ruler. Time becomes a handle on distance because light refuses to change its pace. If that were the only misunderstanding, perhaps it would not matter so much. But the misinterpretation of light years as pure time breeds another idea, one that is even more dramatic and equally wrong, the notion that most of the stars we see in the night sky are already dead. It sounds haunting and grand. People repeat it with a kind of satisfied melancholy. The night sky, they say, is a graveyard. Those stars burned out long ago. We only see their ghosts. It feels like a powerful image. And so it spreads. The problem is that it does not match the actual lifetimes of stars or the distances involved. Most stars bright enough to be seen with the naked eye are relatively nearby in galactic terms. They lie within a few tens, hundreds, or thousands of light years. For a human mind, 1,000 years is colossal. It stretches beyond recorded history and into the fog of myth. For a star, 1,000 years is almost nothing. Stars like our sun live for billions of years. Even larger, shorter-lived stars still burn steadily for millions of years. Seeing them with a delay of a few hundred or a few thousand years is like seeing a person in a photograph taken a fraction of a second ago. When you look up and pick out the bright, familiar points that form constellations, you are not looking at a sky full of stellar funerals already finished. You are mostly looking at ongoing lives, captured slightly earlier in their unfolding. The light has been traveling, the star has been shining. Both truths coexist. The delay is real, but it is not long enough for most visible stars to turn living suns into ghosts. The persistence of that dead star sky image reveals something important. It shows how deeply our sense of time is anchored to human scales. If 1,000 years feels like forever, then 1,000 light years feels like forever multiplied. It becomes easy to imagine that everything at such a distance must already have ended. Yet the universe does not move on human scales. It moves on stellar scales and galactic scales, where 1,000 years is a breath, and 1,000,000 years is only the beginning of a story. These first two misunderstandings, light year as time rather than distance, and sky as cemetery rather than contemporaneity, share a common root. They arise from trying to stretch familiar instincts over unfamiliar territory. When language borrows a word like year and places it inside a new context, the mind drags all its old associations behind it. The word feels known, so the concept is filed away too quickly. To make light years mean what they actually mean, intuition has to be recalibrated. That recalibration is not a matter of memorizing definitions. It is a matter of adjusting the way relationships between time, distance, and light are imagined. One way to do this is to think in terms of delay rather than duration. Picture a lighthouse on a very distant shore, flashing a pulse of light at regular intervals. If you are close, the flashes seem to coincide with the source almost perfectly. If you move far away, so far that light itself needs time to cross the water, you will always be seeing an earlier flash. The farther you are, the more out of date every glimpse becomes. The separation between where you stand and where the lighthouse stands is not only a gap in space, it is a gap in time. A light year is precisely that idea taken to its extreme. It is the delay between emission and arrival when light travels at its fixed speed for 1 year. If a star is 4 light years away, every observation you make of it is 4 years late. If a galaxy is 2 million light years away, every image you capture of it is 2 million years late. The light has crossed the distance. The distance has imposed the delay. The delay has turned space into a record of earlier states. You can also imagine a stream of perfect messages. Each message is a beam of light carrying information about its source. If it takes a year to arrive, the path is a light year long. If it takes 10 years, it spans 10 light years. What is being measured is not how long you think about the message, not how long it matters to you, but how long the universe demands that it travel before it can be received. Time is not telling you how something changes, it is telling you how separated things are. Another analogy sits hidden in the way sound behaves. When a storm rolls across a landscape, you often see the lightning before you hear the thunder. Light reaches you almost instantly. Sound takes longer. For those few seconds, you occupy 2 different times at once. The light is showing you the strike as it was. The rumble is arriving late. If you imagine a world where light was slow in the same way, where you always saw events shifted backward, you have the beginning of the cosmic situation. The lightning is the star. The thunder is the delayed confirmation. The gap between them is a crude echo of a light year's logic. All of this leads quietly to a deeper point. When you hear that an object is so many light years away, there are really 2 statements being made at once. One is about distance, how far the light had to travel. The other is about time, how long that light has been in flight. The misunderstanding occurs when only the time is heard and the distance is forgotten, or when the time is imagined in human terms instead of stellar ones. Correctly understood. A light year is not a lyrical exaggeration, it is a practical necessity. A kilometer is good for roads, 1,000 kilometers for continents, 1,000,000 for orbits. But the distances between stars are measured in trillions of kilometers. Writing numbers that long tells you nothing. They become strings of digits without intuition. The universe forces a shift. Choose a natural ruler that respects the realities of physics. Light provides that ruler. Its speed, multiplied by a year, gives a single, stable quantity that can be used to make sense of otherwise meaningless magnitudes. There is a kind of humility in accepting this. Human culture did not impose the light year on the universe. The universe imposed the light year on human culture. Once you decide to measure the cosmos accurately, you do not get to choose units that flatter your scale. You must choose units that obey the underlying laws. Light travels as it travels. Time passes as it passes. Tie them together, and you get a unit that seems strange at first, only because the world it describes is larger than habit. Seen this way, the early misunderstandings are no longer embarrassing. They are traces of an older relationship with the sky, one in which stars were decorations or omens rather than objects with precise positions in space-time. Thinking of light years as time only makes sense if the sky is imagined as a stage for stories. Thinking of stars as already dead only makes sense if their distances and lifetimes are compressed down into human narrative scales. When the sky becomes an object of measurement, the language has to change. There is a quiet turning point hidden here. The moment you start treating a light year correctly, you stop asking how long until and start asking how far away. You stop projecting yourself into the timeline and start reconstructing the structure outside you. The universe ceases to be a vague backdrop for human events and becomes a system with its own independent geometry. And yet, even with a correct definition in hand, the mind must rearrange itself. It must learn to tolerate the idea that every observation is an observation of the past. It must accept that the stars above are not a live feed, that some of the objects we see may indeed have changed or even ended, not because the sky is full of ghosts, but because time does not stop while light is traveling. The error lies not in thinking change might have occurred, but in assuming that this is the rule rather than the exception. When confusion yields to clarity, another realization emerges. Quieter but more radical to look out into space is always to look back into time. Distance and delay are fused in the concept of a light year so tightly that they cannot be separated. The farther you extend your gaze, the further into history you are forced. Close objects show you a nearly shared present. Distant objects show you an earlier universe. The light year, which first appears as a technical definition, becomes a key to understanding that the sky is not only a map, but an archive. A misunderstanding can be a mirror if you are willing to look into it. Treating light years as pure time reveals how strongly we cling to familiar categories. Imagining most stars as already dead reveals how freely we allow drama to overwrite data. Struggling to picture light traveling for years reveals how small our lifetime is compared to stellar eras. Each incorrect step leaves behind a shadow that outlines the shape of our mental limits. The act of correcting these ideas is not simply an academic exercise. It is the beginning of stretching the mind to match the scales it is trying to contemplate. A light year is the distance between a mission and arrival, the length of a delay imposed by the speed of light, the size of a gap in both space and time between here and there. To hold that definition firmly is to let go of the urge to fold the universe down to human proportions. Amid all the numbers and definitions, a single question quietly remains. If every great distance in the cosmos is written in the time light has been traveling, what does it mean to say that we see the universe at all? Are we looking at what is or at what was, or at an intricate mixture of both that only becomes clear when we accept that distance itself is a kind of memory. The first misunderstandings fall away one by one, and what remains is a sharper, more demanding idea. A light year is not just a way to talk about far-off places. It is a reminder that the universe cannot be described honestly without uniting space and time into a single, continuous fabric. There is a moment in the history of every idea when intuition is no longer enough. Curiosity presses against the edge of what the senses can supply, and the old explanations, once comforting, begin to open into questions they can no longer hold. For the concept of distance in the cosmos, that moment came slowly, across centuries, carried by people who stared at the sky and refused to accept that what appeared constant must be understood only through appearances. Light traveled, stars shimmered, planets wandered, and yet the mechanisms behind these motions remained hidden until someone was willing to think past the surface. In the ancient world, the sky was a dome of symbols rather than a stage for measurement. The Greeks believed the stars were embedded in a crystalline sphere, rotating around Earth with perfect grace. To them, the heavens were polished and immutable. Distance did not matter, because nothing up there changed. What was far could be treated as infinite, and infinite was indistinguishable from fixed. They saw motion, but not travel, brightness, but not delay. And because no one could imagine that light itself needed time to move, the idea of measuring its speed would have seemed unnecessary. Why measure something that appears instantaneous? But questions have a strange way of widening whenever someone notices a contradiction. A simple one emerged first: if the heavens were perfect and unchanging, why did some stars sway in brightness? Why did planets vary in apparent speed? Why did comets trace dramatic arcs across the darkness? As if ignoring the rules, something about the sky was dynamic, and the old model of fixed spheres did not have enough flexibility to explain those changes. The first genuine shift came with the realization that Earth was not the still center of everything. When Aristarchus proposed that Earth moved around the sun, not the other way around. He was reaching for a larger geometry, one that could account for motion without forcing the entire cosmos to spin around a single point. But even Aristarchus knew something was wrong with his own argument. If Earth truly orbited the sun, he reasoned, then the positions of nearby stars should shift slightly as Earth moved, an effect we now call parallax. Yet no such shift could be detected with the naked eye. The silence of the stars became the first great obstacle to the heliocentric idea. And for nearly 2 millennia, that silence was taken as proof that Earth stood still. What no one at the time could appreciate was that the stars did shift. They simply shifted by an amount too small to see. The cosmos was not modestly sized, as intuition suggested, but overwhelmingly vast. The failure to observe parallax was not evidence of a small sky. It was evidence of a colossal sky. Centuries later, the dissatisfaction with old explanations resurfaced. Copernicus resurrected the heliocentric model not because he had seen parallax, but because the mathematical simplicity of placing the sun at the center solved more problems than it created. He sensed a deeper order in the motions of the planets, an order that required letting go of Earth as the center. But Copernicus still lived in a world without telescopes, without precise clocks, without instruments capable of detecting the faint trembling of distant starlight. His model was a conceptual reorientation, not an observational revolution. The observational revolution came next, triggered by something as fragile as glass. In the hands of Galileo, the newly refined telescope became a wedge driven into the old worldview. With it, he saw the phases of Venus, the moons of Jupiter, the mountains of the moon, and the astonishing fact that the Milky Way was not a mist, but a collection of countless stars. The universe expanded under magnification, and a quiet realization began to breathe if stars were not pinpricks on a dome, but suns scattered across depth, then distance, true physical distance, must be vastly greater than anyone had previously imagined. Still, Galileo had no way to measure that distance. He could describe what he saw, but he could not place the stars on a scale, because the scale itself had not yet been invented. The speed of light remained unknown. The size of Earth's orbit was not yet precisely determined, and the techniques to pin down stellar positions were still too crude. Galileo provided evidence for structure, but not for size. The next leap required something stranger than observation. It required patience with the behavior of light itself. In the late 17th century, Ole Rømer, studying the eclipses of Jupiter's moons, noticed a subtle irregularity. The eclipses occurred on schedule when Earth was nearest to Jupiter, but as Earth moved to the far side of its orbit, the events appeared delayed. The moons were not misbehaving, light was. Rømer realized that the only explanation was that light had a finite speed. It took longer to reach Earth when the distance increased by the width of Earth's orbit. With this insight, Rømer became the first person to measure the speed of light in a meaningful way. It was an extraordinary moment. The universe's fundamental velocity was no longer a philosophical guess. It had a value, and once the speed of light had a value, distance gained a new language. Still, the technique was rough, and astronomers needed something more direct, more precise. That precision arrived in 1738 when James Bradley, while searching for the elusive parallax effect, stumbled upon something else entirely: the aberration of starlight, a tiny tilt in the apparent direction of incoming light caused by Earth's own motion through space. Bradley's measurement revealed not only that Earth was moving, which helped silence the old geocentric doubt, but also that the speed of light could be calculated from the angle of this aberration. His result brought the earlier work of Rømer into sharper accuracy. Piece by piece, the ingredients were falling into place. Light had a speed. Earth had an orbit. Stars were spread across depth, not painted on a celestial shell. What remained was to measure the first true parallax, the ancient test that had haunted Aristarchus and limited Copernicus. It took until 1838 for the breakthrough. Friedrich Bessel, using an instrument of remarkable stability, detected a parallax of less than a single arcsecond in the star 61 Cygni. In that minuscule wobble lay the first trustworthy distance to a star. No metaphor can quite capture the delicacy of Bessel's achievement. It was like detecting the shift of a lighthouse thousands of kilometers away by watching how a single grain of dust moves in front of a window. And yet, once the first parallax distance existed, everything changed. The size of the cosmos was no longer a matter of speculation. It had a measurable lower bound. And with that measurement came a problem. The distances were too large for any familiar human unit to be useful. Astronomical units failed at interstellar scales. Kilometers and miles became absurd strings of digits. If humanity wanted to think meaningfully about the universe, it needed a ruler shaped by the cosmos itself. That ruler emerged naturally from the very phenomena scientists had been studying. If the speed of light is fixed, and the travel time of light can be measured, then distance can be expressed as the product of the two. A new unit emerged not from invention but from inevitability: the lightyear. The distance light travels in 1 year. Curiosity had turned into science. Science had turned into measurement. And measurement had turned into a new way of seeing. But this evolution was not simply a chain of discoveries. It was also a change in mindset. Before parallax, the stars were symbolic. After parallax, they were spatial. Before Rømer, light was an abstraction. After Rømer, it had speed, delay, and consequence. Before telescopes, the sky was smooth. After telescopes, it was layered with depth and motion. Each tool reshaped not just what humanity could see, but what it believed could be known. With each generation, the mental model of the universe expanded. The cosmos grew larger not because it changed, but because human perception learned to accommodate its scale. This was not an easy expansion. Every time the horizon widened, there was a quiet resistance, an instinctive desire to return to what felt proportionate, manageable, comprehensible. The trick was not merely to accept new measurements, but to internalize them, to let them reshape intuition. Some of the earliest debates reveal how hard this internalization was. When Galileo saw that Jupiter had moons, he was not simply discovering new worlds. He was undermining the idea that Earth held a privileged position. When rumor announced that light had a speed, he was not simply measuring a constant. He was undoing the belief that celestial motion must be perfect and instantaneous. When Bessel detected parallax, he was not simply mapping a star. He was forcing humanity to confront distances so vast that ordinary numbers broke under them. Understanding required a shift in imagination. The sky had to be seen as three-dimensional. Time had to be seen as intertwined with distance. Light had to be seen as a messenger with a finite pace. Errors that once seemed justified dissolved into new clarity, and the cosmos that emerged was larger, older, deeper, and stranger than anything earlier cultures had allowed themselves to believe. But the story of curiosity turning into science does not end with the 19th century. Once humanity learned to measure the distance to nearby stars, it wanted to push further, to reach past the limits of parallax. Larger instruments were built. Astronomers learned to measure brightness and spectral signatures, and new methods, standard candles, variable stars, redshift, were developed to extend the cosmic distance ladder. Light years multiplied from tens to thousands to millions to billions. Embedded in this progress was a subtle transformation. As scientists extended their reach outward, they were not just measuring distances, they were reconstructing the past. Every additional light year pushed the window of observation further back in time. Measurements became a dialogue with history. To know how far away something was became synonymous with knowing how long its light had been in transit. Space became a chronology. Telescopes became time machines. And each improvement in technology allowed observers to peel back another layer of the universe's early story. The consistency of light's speed became the backbone of cosmic investigation. It provided the link between what could be seen and what could be inferred. The fact that light traveled at a fixed pace meant that brightness, color, position, and movement all encoded information about distance and motion. Astronomers were no longer merely watching the sky. They were decoding it. That decoding demanded not only skill, but imagination. Even after Bessel's parallax measurement, the scale of the galaxy remained elusive. William Herschel had tried to estimate its shape decades earlier, counting stars in different directions. But his model was distorted because he did not yet understand how dust absorbed light or how stellar brightness varied. Only with the advent of new methods in the 20th century did astronomers uncover the true scale of the Milky Way. And with it, the realization that our sun was not near the center, but adrift in one of the galaxy's outer spiral arms. Knowledge expanded outward, but it also expanded inward. For as distances grew, so did the humility required to contemplate them. The light year, once a curiosity, became a tool for grounding the mind in realities so large that intuition alone could not handle them. It transformed from a definition into a lens, one that forced observers to confront the profound age and scale of the cosmos. Even Einstein's work, which reshaped the relationship between space and time, relied on the constancy of light's speed as a principle. Without that constant, relativity collapses. With it, new structures form time dilation, length contraction, the merging of time and space into space-time. In a sense, the light year foreshadowed relativity long before Einstein formalized it. It quietly encoded the rule that time and space are not separate categories but reflections of each other, joined through the motion of light. By the time modern astronomy emerged, the The transformation was complete. Humanity had passed from metaphor into measurement, from seeing stars as symbols into seeing them as coordinates in an expanding, evolving universe. The light year became the bridge that made this comprehension possible. It translated the impossible into the measurable and the immeasurable into the conceivable. Yet behind all of this progress lies a reminder of where the journey began with confusion. Not because people were foolish, but because the cosmos is not designed to fit the scale of human life. Misinterpretation was a natural consequence of living inside a world calibrated to footsteps, not to photons. The triumph of science was not only in building telescopes or refining mathematics, it was in learning to think past instinct, to allow the universe to teach its own rules rather than forcing human rules onto it. Every advance in measuring cosmic distance has been, at its heart, an act of humility. It required the willingness to be wrong, to correct old ideas, to accept that the universe is stranger than first impressions suggest. And each correction opened the way to a larger view, a clearer structure, a deeper sense of place. By the time the term light year entered scientific language, the intellectual landscape had already changed. The tools had matured, the models had expanded. The curiosity that once strained against the limits of perception had finally found a way to map the darkness. From that point forward, everything humanity learned about the universe, its age, its expansion, its structure, depended on the ability to measure distances. Measured not in meters, but in years of light's travel, curiosity had become science. And science had become the key to unlocking the architecture of the cosmos. But measurement is only the beginning. Once you know how far away something is, the next question is inevitable. What lies in the spaces between? What fills the void from star to star? What invisible structures govern the behavior of light as it travels across those unfathomable distances? The first real sense of cosmic distance does not come from the far edges of the universe. It comes from something much closer. Something small enough to appear familiar, yet large enough to reveal how profoundly scale can distort intuition. It begins with our own solar system, with the quiet realization that the neighborhood around the sun is already far larger than anything the human mind is naturally prepared to imagine. Before contemplating galaxies millions of light years away, one must learn to understand what it means for a single beam of light to cross the spaces between planets. The solar system seems compact when drawn in textbooks or imagined from childhood diagrams. A bright sun in the middle, a ring of planets orbiting neatly, a few dotted moons circling them, perhaps a comet sweeping by in a graceful curve. The model feels complete, almost cozy. But that comfort dissolves when the distances are treated honestly. The space between planets is not a gentle spacing of neighbors. It is a desert of scale, a silence so enormous that light, fast, relentless, unstoppable, requires minutes or hours to cross it. Consider a simple example. The light from the sun takes just over 8 minutes to reach Earth. That interval is small enough to be forgotten, but the distance it represents is anything but small. Those 8 minutes correspond to about 150 million kilometers, a number so large that it only becomes meaningful when tied again to the speed of light. If light required 8 minutes to arrive, then communication, sight, and every form of electromagnetic awareness we possess is delayed by 8 minutes when looking toward the sun. The sun you see is never the sun that exists now. It is the sun of 8 minutes earlier. That delay grows dramatically as one moves outward. To see Mars is to see a version of Mars from a few minutes to more than 20 minutes ago, depending on where the two planets are in their orbits. To see Jupiter is to peer almost an hour into the past. To see Saturn is to look back more than an hour. These numbers may sound modest, but each represents a gulf so wide that the very concept of nearby begins to lose coherence. Even spacecraft, engineered to cross distances at unimaginable speeds compared to human standards. Face these separations with stark humility. When the Voyager probes send signals back to Earth, those signals take more than 20 hours to arrive. 20 hours for a beam of radio light, traveling at the same speed as any photon, to cross the dark stretch that separates a tiny, aging spacecraft from home. By the time mission controllers hear from Voyager, the spacecraft has already changed, drifted, aged, moved. Every instruction sent must account for the delay. Every confirmation received is a message from yesterday. It is in these planetary distances that understanding first begins to alter perception. The solar system stops being a diagram and becomes a structure, a real architecture measured in minutes and hours of light's travel. When a single hour of photon flight corresponds to the gap between worlds, the meaning of a light year becomes easier to sense. A light year is not simply a large number. It is a scale transformation so complete that it requires shrinking the solar system into something barely visible. Scientists often use analogies to bridge this gap, not as decoration, but as scaffolding for intuition. One analogy imagines the sun as a ball the size of a large lamp, and Earth as a grain of sand several meters away. In this model, Mars is another grain a few meters farther, and Jupiter is a pebble tens of meters beyond that. The outer planets drift so far into the distance that a person must walk across a field to place them correctly. The solar system becomes a long, thin corridor, mostly empty, with its objects reduced to small points that barely interact except through gravity and light. Another analogy compresses the scale so that the distance between the Sun and Earth is the width of a human palm. In that version, Jupiter lies at the elbow, Saturn near the shoulder, and the outer planets disappear into the hallway or the next room. The edges of the solar system, particularly the region known as the Oort cloud, extend so far that on this scale they would be kilometers away. Even the nearest star, Proxima Centauri, would be positioned thousands of kilometers from the Sun's location. The solar neighborhood transforms from an intuitive cluster into an archipelago separated by oceans larger than any world can truly contain. These analogies reveal something subtle. The solar system contains almost no matter. It is mostly emptiness, structured by gravity and illuminated by light. The objects we think of as dominant, the planets, are tiny compared to the space between them. Light moves freely through these gulfs, but not instantly, and so the emptiness has a measurable size. This sense of scale began to sharpen historically as astronomers learned more about the motions of the planets. Johannes Kepler, through careful analysis of Tycho Brahe's observations, discovered that planetary orbits were not circles but ellipses. This insight suggested a dynamic, mathematically coherent system, one in which distance changed constantly as each planet swept through its path. Isaac Newton later showed that these motions could be derived from universal gravitation, turning the solar system into a solvable structure rather than a collection of mysterious wanderers. With Newton's laws, the relationship between mass, distance, and motion became quantifiable. The solar system was no longer a set of lights in the sky. It was a machine whose pieces interacted through forces that extended invisibly across space. Distances mattered in those equations. They were not decorative. They determined orbits, energies, and the stability of the entire system. Yet Newton himself did not know the scale of the solar system with precision. His equations worked, but the actual size of Earth's orbit, known as the astronomical unit, was still being refined. Measuring it required more than geometry. It required capturing the parallax of Venus during a rare transit across the Sun. The 19th century expeditions sent across the globe to observe, these transits were not chasing a spectacle, they were chasing accuracy. By comparing observations from different latitudes, astronomers could compute the true Earth-Sun distance and thereby calibrate the entire solar system. Once that calibration existed, Every distance in the solar system became expressible in meaningful numbers. But as soon as those numbers were understood, they pointed toward a startling realization: even the nearest stars lay far beyond anything planetary measurement could handle. The solar system, with all its emptiness and enormous scale, was only a small bubble in a far greater ocean. That ocean begins at the boundary where the sun's influence fades. Beyond the orbits of the known planets lies the Kuiper Belt, a region populated by icy remnants of early formation. Beyond that lies the Oort cloud, a roughly spherical shell of frozen bodies, stretching perhaps a light year from the sun. It is not uniformly filled, but its outer boundary marks a conceptual threshold. A light year is not an abstract creation. It is roughly the distance at which the sun's gravitational hold weakens enough for the Milky Way to dominate. In this way, the nearby worlds serve as a bridge. They show how light measures space, how gravity structures it, and how distance reshapes everything from communication, time, to orbital mechanics. They also reveal something more delicate: the solar system is not static. Its objects move. Their shadows shift. Their positions change during the time it takes light to travel between them. Even simple observations require accounting for the fact that now cannot be shared across distance. One of the most striking examples of this came from the early days of interplanetary missions. Engineers guiding spacecraft had to anticipate where a planet would be when the craft arrived, not where it appeared when the mission launched. If Earth sends a probe toward Mars, the light from Mars that Earth sees might be several minutes old. By the time the spacecraft reaches the vicinity of Mars, the planet will have moved along its orbit. Navigators must aim not for the visible world, but for the predicted world. Distance becomes a conversation between observation and expectation. The farther missions traveled, the more dramatic this became. When Voyager 1 performed its famous flyby of Jupiter, the images it returned were already hours old by the time scientists saw them. When it photographed Saturn, the delay stretched even further. Once Voyager photographed Neptune, the outermost planet it would visit, its images were traveling more than 4 hours through space to reach Earth. Imagine watching an event unfold on a screen where every change is delayed by the distance light must cross. That is the reality of exploring nearby worlds. These delays become even more striking when considered in reverse. When Earth transmits commands to a distant spacecraft, those commands also take hours to arrive. A correction sent too late cannot prevent an error already committed. A maneuver executed must be done blindly, without real-time feedback. Interplanetary navigation is therefore built not on reaction, but on anticipation, on understanding how distance shapes communication. The solar system forces an awareness of time woven through every calculation. This interplay between distance, delay, and prediction creates a kind of choreography, one in which each planet plays its part. Light becomes the scorekeeper, revealing how long each step takes between worlds. And it becomes clear that even within the sun's domain, space is not merely large. It is structured by speeds and intervals that carve time into the architecture of movement. The nearby worlds also teach something else: that distance transforms not only travel, but perception. When spacecraft first approached planets, the familiar points of light swelled into landscapes. Jupiter's storms resolved into swirling vortices. Saturn's rings revealed intricate patterns of icy debris. Pluto, once a blur, became a world of jagged mountains and frozen plains. When New Horizons arrived in 2015, each encounter was a reminder that the concept of near is subjective. A planet may be close in cosmic terms and yet separated from us by billions of kilometers. These revelations carry philosophical weight. They suggest that proximity is not simply physical, but perceptual. A world remains unknown until one gets close enough for light to return detailed images, and close enough is a relative measure defined by the tools available. In this sense, distance is not an obstacle, but an invitation to expand awareness. As humanity learned to explore these nearby realms, another pattern emerged. The farther one travels from the sun, the more the nature of light changes. Near Earth, sunlight is intense, casting sharp shadows and driving weather. Near Jupiter, the light is dimmer, gentler, unable to illuminate the gas giant's deeper layers without help from instruments. Near the Kuiper belt, sunlight is so faint that a midday sky would resemble perpetual twilight. At the edge of the Oort cloud, light from the sun is a whisper, a faint memory of brightness. This gradual fading shows how the light year begins locally, not as a distant abstraction, but as a transformation in the familiar. The sun, which dominates our sky, becomes a star among stars as one moves outward. The idea that other suns likely have their own planets becomes intuitive once we see how our own system behaves at scale. Distance reveals symmetry, and that symmetry expands imagination. The study of nearby worlds did more than refine measurements. It altered the narrative of existence. The discovery of moons around Jupiter suggested that Earth was not unique in hosting systems of smaller bodies. The presence of rings around Saturn, Uranus, and Neptune implied that planetary systems could exhibit recurring structures. The detection of exoplanets in recent decades confirmed that our solar system is only one arrangement among countless others. These recognitions form a chain that leads inexorably outward. If the solar system is not unique, then the distances between stars become more than empty gulfs. They become pathways between possible worlds. If light can carry images across minutes, hours, and eventually years, then observing distant stars becomes an act of reading the universe's autobiography. Yet all of this begins with understanding the scale of our own neighborhood. Without internalizing planetary distances, the meaning of a light year remains abstract. Once those distances are felt, once one senses how long light takes even to cross the solar system, then a light year becomes something real. Not a linguistic curiosity, but a physical interval the mind can begin to respect. And in this respect, the nearby worlds offer something almost poetic. They show a gradient of difficulty. Reaching the moon required days. Reaching Mars required months. Reaching Jupiter required years. Each step outward increased the gap, not by addition, but by multiplication. Human missions represent determination, expanding into distance, and each crossing demonstrates how the scale of the cosmos resists shortcuts. In contemplating these worlds, one also begins to understand that the solar system is the boundary between planetary clarity and stellar mystery. Within it, light travel times are measured in minutes and hours. Beyond it, the unit expands into years. The transition from hours to years is not merely a jump, it is a threshold, a doorway into the domain where the light year becomes necessary. By exploring the solar system, humanity learns something essential about itself. The desire to reach outward persists even when the scale becomes daunting. Curiosity continues even when the distances stretch into intervals that no person will ever traverse physically. In every mission, every measurement, every image returned from the darkness, there is a reminder that understanding requires more than proximity. It requires patience with the universe's vastness. And so, the nearby worlds become a prelude to the greater distances beyond. They are the foothills before the mountains, the opening lines before the epic. They show that even in our own cosmic backyard, distance has weight, light has duration, and the universe does not reveal itself all at once. There comes a point in the story of distance where the limits of human reach become undeniable. The solar system, immense as it is, still permits exploration by spacecraft, still allows physical probes to cross its inner regions and send home delayed signals from the outskirts. But the moment we step beyond that boundary, beyond the faint gravitational breath of the sun, the universe ceases to be a place we can touch. It becomes something we must infer. The transition is not merely technological, it is conceptual. When distances expand from hours of light travel to years and then to millennia, the act of knowing shifts from contact to interpretation. The nearby worlds could be visited. The stars cannot. And so, astronomy transforms from navigation into detection, from travel into reading the faintest traces of light. The abilities that let us detect the invisible were not granted all at once. They emerged across centuries of refinement, shaped by questions that demanded sharper instruments and minds patient enough to listen to the universe's subtler signals. The eye, which once dominated our understanding of the sky, proved insufficient, not because it lacked sensitivity, but because the cosmos speaks in a language broader than visible light. To detect the structure of reality across light years requires attending to every wavelength, every shift, every encoded pattern carried by the photons that survive their passage through space. The first step in detecting the invisible begins with recognizing that stars, though they appear as tiny points, carry information in their brightness. Not the brightness itself, but the way it varies. Astronomers learned early that some stars pulse, expanding and contracting like slow cosmic heartbeats. Henrietta Leavitt, studying these variable stars, discovered a relationship between the period of their pulsation and their intrinsic brightness. This allowed astronomers to compare apparent brightness to true brightness and infer distance. Suddenly, stars that would otherwise sit isolated in darkness gained measurable locations. A light year became not an abstraction, but something calculable from rhythms written into starlight. This method thrives on precision, a variation by a fraction of a percent. A shift in timing by a single hour becomes the basis for mapping galaxies. At the time, it must have felt like learning to navigate an ocean by listening to the faintest repetition of waves rather than relying on direct vision. The cosmos offered signals so delicate they could only be trusted when observed with discipline, consistency, and instruments that refused to lie. As telescopes improved, astronomers turned to a deeper signature, the color of starlight. A star's light, when spread into a spectrum, reveals dark lines, gaps where atoms in the star's atmosphere absorb specific wavelengths. Each element produces its own pattern, like a chemical fingerprint. These absorption lines let astronomers determine a star's composition, temperature, density, and, crucially, its motion relative to Earth. When a star moves away, its spectral lines shift toward the red. When it approaches, they shift toward the blue. This Doppler effect, simple in principle, became a cornerstone of cosmic measurement. It allowed scientists not only to detect motion, but to measure velocity across incomprehensible distances. Suddenly, the universe was not static. It was in motion everywhere. Stars drifted in orbits around the galaxy. Galaxies moved apart. Clusters expanded. And, by tracking these motions, astronomers could infer distances without ever touching the objects themselves. A light year was not just the travel time of light. It was intertwined with velocity, expansion, and the geometry of space-time. These early spectral techniques opened a doorway into the invisible, but they were only the beginning. Soon, astronomers realized that starlight interacts with matter in ways that reveal what cannot be seen directly. Dust between stars absorbs particular wavelengths, reddening distant objects. Gas clouds emit light at distinct frequencies, marking their location. Even the absence of light, regions where starlight is blocked, can indicate the presence of cold molecular clouds where stars may eventually form. Light became a messenger fluent in nuance. It carried shape, composition, history, and motion. The discovery of radio waves arriving from space expanded this language dramatically. Unlike visible light, radio waves can pass through dust, revealing structures hidden behind veils of opacity. The Milky Way, once assumed to be a relatively simple disk, unfolded into a swirling pattern of spiral arms. When observed in the 21-centimeter hydrogen emission line, that single wavelength, produced by a flip in the spin state of hydrogen atoms, mapped the structure of our galaxy far beyond what optical telescopes could accomplish. Hydrogen, the most abundant element in the universe, had become a lantern illuminating the invisible architecture of the cosmos. The ability to detect radio waves also unveiled unexpected phenomena. Pulsars, rapidly spinning neutron stars, announced their presence through rhythmic bursts of radio light. Quasars, distant active galactic nuclei powered by supermassive black holes, shine in radio with such intensity that their signals cross billions of light years. These discoveries required no movement on humanity's part. They required listening. The cosmos, overflowing with events too violent, too distant, or too faint to be seen, became accessible through instruments that transformed radio waves into meaning as wavelengths broadened into microwaves. One of the most profound observations in the history of science emerged the cosmic microwave background. This faint afterglow, spread across the sky, is light from when the universe was only 380,000 years old. Its uniformity and slight variations provide a map of the early cosmos, a snapshot of matter just as it became transparent to light. To detect this whisper from the beginning of time required instruments sensitive enough to register differences in temperature of a few millionths of a degree. The light year, by this stage, had expanded beyond a unit of distance. It had become a measure of how far back one could see, or rather, how far light had carried information before being released into the openness of space. Infrared astronomy brought another transformation. Dust that blocks visible light often glows gently in infrared wavelengths. Regions that appear dark in optical images, stellar nurseries, the centers of galaxies, and the cores of collapsing clouds, become luminous in infrared. This allowed astronomers to peer into the birthplaces of stars, to watch the early stages of planetary formation, to study the hidden dynamics of galaxies. Infrared light communicates warmth, structure, and emergence. It shows not only where stars are born, but where light begins its own journey across time. X-ray astronomy revealed the opposite places where matter falls into gravitational wells so deep that it heats to millions of degrees, around black holes, neutron stars, and supernova remnants. X-rays flare with intensity. They betray the presence of objects so dense and extreme that they cannot be seen directly. Detecting X-rays requires telescopes placed in orbit, because Earth's atmosphere absorbs them. A fortunate barrier for life, but an obstacle for observation. Once instruments were lifted above this shield, the universe unveiled its fierce and violent side. Collisions, accretions, explosions, all events where matter is compressed into unimaginable conditions, became visible. These observations mapped not the calm glow of stars, but the turbulence of cosmic evolution. Gamma-ray astronomy reached even further into the extreme. Gamma-ray bursts, the brightest explosions since the Big Bang, shine for seconds or minutes and then disappear. Their light travels across billions of light years, carrying the story of stars collapsing into black holes or merging into neutron stars. Without instruments capable of catching such fleeting flashes, these events would remain unknown. The detection of gamma rays, with their penetrating but infrequent arrivals, transformed the understanding of cosmic death and rebirth. All these wavelengths, radio, microwave, infrared, optical, ultraviolet, X-ray, gamma ray, form a spectrum that encodes the universe's structure. Together, they allow astronomers to reconstruct distances, masses, temperatures, motions, and histories. Light becomes not only a traveler, but a document, recording the conditions of everything it touches. The light year is the page on which these records are written, but some things remain invisible even to this expanded sensorium. Dark matter, which shapes the motion of galaxies, emits no light. Dark energy, which drives the accelerating expansion of the universe, leaves no direct signature in photons. To detect forces that do not interact with light requires another approach entirely, one that looks at motion rather than illumination. By studying how stars orbit within galaxies, astronomers infer the presence of matter they cannot see. The stability of galactic clusters, the bending of light by gravitational lenses, the distribution of cosmic structures, all point to hidden mass. The light year remains relevant even here, for distances must be known to interpret gravitational effects. The invisible becomes detectable through its influence on the visible. In 2015, the first direct detection of gravitational waves further expanded the toolkit for detecting the unseen. These ripples in space-time, produced by collisions of massive objects like black holes or neutron stars, travel across the universe at the speed of light. They are not light themselves, but they carry information analogous to it. Gravitational waves pass through matter effortlessly, arriving from sources unreachable by photons. Their detection required instruments capable of measuring changes smaller than 1/10,000th the width of a proton. With each event measured, astronomers opened a new sense, one that hears the universe through its vibrations rather than through its illumination. This layering of senses, light across wavelengths, motion through Doppler shifts, structure through gravitational effects, and cosmic tremors through gravitational waves, forms the foundation of modern astronomy. It allows humanity to construct a map of the cosmos, not by traveling to distant places, but by reading the messages arriving from them. Yet the process is not simply technical, it is interpretive, requiring imagination tethered to evidence. The universe sends signals, but they must be translated, understood, contextualized. The concept of a light year becomes central in this translation. It is the ruler by which the placement of every observation is judged. The light from a galaxy 10 million light years away tells us what that galaxy was doing 10 million years ago. The radio pulse from a distant pulsar reveals not only its spin, but also the distance its signal crossed. The color of starlight shifts in a way that corresponds to velocity and distance. Each observation rests on travel time. Each interpretation relies on knowing how far the light has come. To detect the invisible, one must first accept that the universe reveals itself slowly, not because it withholds truth, but because its truths are carried across distances too vast for immediacy. When telescopes gather photons that began their journey before humans existed, they are not capturing the present, they are capturing the archive. Distance becomes chronology, and every light year becomes a measure of how far back into that archive one can reach. The James Webb Space Telescope, launched with the capacity to see in infrared with unprecedented clarity, expanded this archive dramatically. Its images show galaxies so distant that their light left them more than 13 billion years ago. Structures formed when the universe was only a few % of its current age appear with crisp detail. Webb does not look farther in space, it looks farther in time. The distinction matters. Other galaxies are not physically closer or farther in any traditional sense. They are younger or older in the light they release. The telescope functions like a historian equipped with a new method for reading ancient texts, capable of interpreting older and fainter pages of the cosmic record. Detecting the invisible also raises a philosophical tension. How much of the universe can ever be known? The observable universe is limited by the distance light has traveled since the Big Bang. There are regions forever beyond reach, expanding away faster than light can cross the gap. No instrument, no matter how powerful, can detect what lies beyond that horizon. The light year thus defines not only distance but boundaries, limits on knowledge imposed by the structure of space-time itself. Yet within these limits, the act of detection becomes deeply human. It requires patience, creativity, and an acceptance that learning often means letting something reveal itself over long intervals. The signals we receive today are echoes of processes that unfolded across billions of years. To detect them is to engage in a dialogue with the past, to listen to messages written before Earth existed. In this way, the universe does not hide its invisible structures out of secrecy. It hides them behind distance. To learn to detect the invisible is to learn to interpret faintness, to amplify whispers, to reconstruct entire scenes from fragments of arriving light. The cosmos becomes a vast auditorium where every wavelength plays a different instrument. Together, they form the symphony of existence, and astronomy becomes the art of listening closely enough to understand the score. The transition from Act 4's tangible worlds to Act 5's invisible structures shows how distance transforms method. Within the solar system, seeing and measuring were straightforward. Beyond it, the universe becomes an interpretive field, one where distance dictates which senses can reach. And as those senses broaden, so does the definition of what it means to observe now. One final question hovers as this act draws to a close. If light and gravity and waves have revealed so much, what happens when we follow those signals outward? Into the domain where stars multiply into billions and galaxies form the patterns of the deep universe. There is a moment in the study of distance when the solar system finally recedes into something small, almost fragile, like a lantern hanging in the corner of a much larger room. The sun, once the dominant presence in the sky, becomes just one star among hundreds of billions. The planets shrink into shadows, orbiting a glow that is no longer central, no longer unique. As awareness expands outward, the structure of the Milky Way begins to emerge, a disk of stars stretched across space like a luminous river, spiraling in long, graceful arms that move so slowly no human being could ever witness their rotation. To enter this realm is to step into an ocean so vast that every measurement must be carried by light years, because no lesser unit can hold the magnitude. The first impression of the Milky Way is always deceptive. From Earth, it looks like a hazy band, faint enough to be drowned out by artificial light, yet rich with detail when seen under a dark sky. For most of human history, it was assumed to be a cloud, a mist, a smear of celestial vapor. But when Galileo turned his early telescope toward it, the smear dissolved into countless individual stars. That single observation rewrote the scale of the known universe. It was not a cloud at all. It was a structure. And if it had structure, then it must have size. But how large? How far did the star river extend? How deep was its current? The answer could not come immediately, because the stars refused to reveal their distances. They sat scattered across the sky with no hint of depth. Only brightness could be measured. And brightness alone is deceptive. A faint star might be dim because it is small, or because it is far away, without knowing which. The mind cannot place it in three-dimensional space. It is like looking at a city at night from a distance. Every window glimmers, but the skyline is flat. Yet, even before the tools emerged to measure individual distances, astronomers sensed that the Milky Way must be enormous. The density of stars in the band suggested that we were inside something, not outside it. The darkness above and below the band suggested that the structure was a disk rather than a sphere. But the true understanding of scale required new methods, new interpretations of starlight. The breakthrough began with variable stars, particularly Cepheid variables. Henrietta Leavitt's discovery that the period of their pulsation correlates with their intrinsic brightness provided a standard candle, an object whose true luminosity could be known. With that knowledge, distance could be inferred by comparing what the star should look like to what it actually looked like. Suddenly, depth became measurable. The Milky Way unfolded from a blur into a layered space. Measurements revealed something astonishing. The galaxy is more than 100,000 light-years across. A beam of light. Swift. Unwavering. Traveling at the universe's maximum speed. Would require 100 millennia to cross from one side to the other. Every structure within it, from spiral arms to star clusters, exists on timescales deeper than human imagination. The Sun orbits the galactic center once every 230 million years. In the entire history of complex life on Earth, the solar system has made one orbit and begun another. As the galaxy's scale becomes clear, a profound shift occurs. Stars cease to be isolated points and become citizens of a vast, gravitationally bound community. Their motions trace arcs around the galactic center, pulled by forces that reach across thousands of light years. The Milky Way becomes not a background, but a dynamic organism, constantly reshaping itself as stars live, die, drift, collide, and are born again from the remnants of earlier generations. But even this understanding contains deeper layers. The distribution of stars suggests a spiral structure, but mapping that structure requires more than optical observation. Dust between stars obscures light, reddening it and dimming it. To peer through this haze requires infrared and radio wavelengths. When astronomers observed the galaxy in the 21-centimeter hydrogen line, the spiral arms became unmistakable. They were not decorative swirls, but the gravitational imprint of density waves. Regions where matter accumulates and starlight thickens. These arms extend like currents in an ocean, sweeping stars along in slow rivers of orbiting light. The Sun sits not in a major arm, but in a minor spur called the Orion Arm, a quiet neighborhood compared to the grand structure of Sagittarius and Perseus. And yet, even this modest position contains wonders star-forming regions. Clusters of young blue giants, molecular clouds where new suns sleep inside cocoons of dust. The more one studies this galactic ocean, the more the light year becomes essential. Every feature, every drift, every connection between stars must be expressed in terms of how long light travels. A star 2,000 light-years away is distant enough that the photons reaching us tonight departed when ancient civilizations were only beginning to carve their marks into stone. A cluster 10,000 light-years away shows us its appearance from a time when humans had not yet learned to write. The galaxy becomes a mosaic of eras layered across thousands of centuries, all visible at once. As astronomers pushed outward, they discovered something even more surprising. The stars in the outer parts of the Milky Way move too quickly to be accounted for by the visible mass alone. According to classical physics, stars on the edge should orbit more slowly than those near the center, just as planets do in the solar system. But observations showed that their velocities remained nearly constant. The outer stars moved faster than they should, as if held in place by a gravitational force that could not be seen. This discrepancy led to one of the most important concepts in modern astrophysics, dark matter. Though invisible in every wavelength, dark matter exerts gravitational influence on stellar motions. It forms a halo around the Milky Way, extending far beyond the visible disk. Its presence can be inferred only through its gravitational pull, detected by watching how stars orbit in defiance of expectations. In this way, even the unseen becomes part of the cosmic map, woven into the distances defined by light years. Dark matter reshapes the galaxy's identity. No longer merely a disk of stars, the Milky Way becomes a structure embedded in a larger, invisible framework. The true diameter of the galactic halo may stretch hundreds of thousands of light years, dwarfing the luminous disk at its core. If the visible galaxy is a glowing island, then dark matter is the ocean in which it floats. This ocean is not still. It contains currents of stars stripped from small galaxies that pass too close, tidal streams marking ancient collisions. The Milky Way has absorbed dozens of dwarf galaxies across its history, and their remnants still arc through the halo like faint ghost rivers. These streams can be detected through careful measurements of stellar motion. Their patterns reveal how the galaxy grew, how its spiral form was shaped by gravitational encounters. The most dramatic of these interactions is still in progress. The Andromeda Galaxy, more than 2 million light-years away, is on a collision course with the Milky Way. The two galaxies move toward each other at hundreds of kilometers per second. Though the motion is irrelevant to human timescales, the collision will occur in about 4 billion years, long after the Sun has changed profoundly. But the light we see from Andromeda tonight shows it as it was millions of years before the first humans walked upright. Distance compresses epochs, turning cosmic evolution into a tapestry of overlapping timelines. To appreciate the scale of 1 million light-years is to confront the limits of intuition. 1 million years exceeds not only recorded history, but the entire existence of Homo sapiens as a species. And yet, light crosses that distance steadily, carrying images of other galaxies, each containing billions of stars. The number of galaxies visible to modern telescopes extends into the hundreds of billions. The observable universe contains more stars than there are grains of sand on all the beaches of Earth. A comparison so vast that merely stating it forces the mind to stretch. But the ocean of stars is not uniform. It has filaments and voids, walls and clusters. On scales larger than galaxies, matter forms cosmic webs, strands of dark matter guiding the distribution of luminous matter. Galaxies gather in clusters. Clusters form superclusters, and superclusters form the filaments that span hundreds of millions of light years. The distances involved are so great that light's travel becomes the only reliable way to conceptualize them. Between clusters lie voids, regions so empty that a beam of light could travel for hundreds of millions of years without encountering a single galaxy. To detect these structures required studying not just individual stars or galaxies, but their collective light. When telescopes surveyed large regions of the sky, patterns emerged: arcs, sheets, and knots of illumination. These were not random. They reflected the evolution of matter under gravity, tracing the expansion of the universe itself. Standing inside this architecture, the Milky Way appears as one thread in an unimaginable tapestry. Its spiral arms, its clusters, its halo, all become small components of a structure whose dimensions dwarf the galaxy in every direction. And yet, despite the enormous scales, the light year remains the universal measure. It provides a consistent way to describe everything from the separation between stars to the distance between superclusters. It is the unit that binds together the near and the far, the modest and the colossal. Even within the Milky Way, light years define the relationships between stars. Our nearest neighbor, Proxima Centauri, lies a little more than 4 light years away. This distance is small by galactic standards, but vast by human ones. At this scale, the solar system becomes a speck, a local feature in a field extending thousands of times further in every direction. The distance to Proxima is enough to remind us that interstellar travel, even at speeds achievable by spacecraft, would require tens of thousands of years. The ocean between stars is not filled with physical barriers. It is shaped by time. The mind must change shape to inhabit these dimensions. It must learn to picture distances not as lines on a map, but as histories. The light from a star is not merely distant, it is old. The light from a galaxy is ancient. The farther one looks, the deeper into time one must peer. The Milky Way becomes not only a structure, but an archive, with each distance marking a page in the unfolding story of the cosmos. In this archive, some pages are bright and recent, written by stars relatively close to the Sun. Others belong to distant clusters whose light left them long before Earth existed. Still others belong to galaxies whose appearance tonight is a remnant from a universe that was smaller, denser, and younger. The light year becomes the scale on which history is measured, allowing astronomers to reconstruct how the cosmos has changed across billions of years. In contemplating this ocean of stars, a quieter realization surfaces. The universe is not static. It is not a picture frozen in space. It is a process, ongoing and dynamic. Stars form, evolve, and die. Galaxies collide and merge. The cosmic web stretches as expansion accelerates, and all of this motion is written into the light that travels to us. To study distance is to study change. Yet, despite its vastness, the Milky Way holds a particular intimacy for humanity. It is the galaxy that shaped the conditions for life on Earth. Its arms contain the heavy elements forged in earlier generations of stars. Its spiral structure creates regions of density that lead to new star formation. Its halo protects the disk from disruptive intruders. Even as one contemplates the immensity of the cosmic ocean, the Milky Way remains a place, a home, not through proximity, but through belonging. Every atom in the human body was formed in the explosions of stars scattered across this galaxy. Distance does not diminish that connection, it defines it. The study of the Milky Way required centuries of observation and interpretation. It demanded that astronomers accept that their senses were insufficient. They had to listen to the universe in wavelengths beyond vision, to read patterns invisible to the naked eye. The journey from Galileo's first glimpse of the star river to today's detailed maps of the galactic disk is a triumph of curiosity, patience, and the willingness to revise assumptions. As understanding deepens, the galaxy transforms from a backdrop into a structure with layers, complexities, and histories. Its stars populate a disk, a bulge, a halo. Its dark matter outlines a larger form. Its arms trace the rhythms of matter flowing under gravity. And across its vast expanse, the light year serves as the measure of every separation, every journey, every connection. When one steps back and looks at the entire arc of knowledge, from ancient interpretations to modern surveys, it becomes clear that the meaning of distance has changed profoundly. A light year is no longer simply the distance light travels in 1 year. It is the currency of cosmic understanding, the scale on which the universe writes its biography. As the ocean of stars recedes into perspective, another kind of distance begins to stir at the edge of understanding, an unsettling distance, one that does not behave like the simple stretches between worlds or even the spiraling gaps between galaxies. Up to this point, distance has been an interval that light eventually crosses, a separation that simply demands time. But beyond the Milky Way, beyond the clusters and superclusters, and even beyond the great filaments of the cosmic web, the structure of reality itself begins to twist around the very concept of separation. It is here, in the deep dark between galaxies, that we encounter the paradoxes that challenge intuition, distances so immense that they reshape not only travel, but causation, not only measurement, but meaning. The first paradox emerges quietly, not from speculation, but from observation. When Edwin Hubble measured the redshift of distant galaxies, he discovered that their light was stretched, shifted toward longer wavelengths, not because the galaxies themselves were moving through space at those speeds, but because the fabric of space between us and them was expanding. Light, traveling across millions of light years, lengthened as the space it crossed stretched beneath it. This was not motion in the ordinary sense. It was the universe itself changing scale. This discovery carries a subtle but profound implication the farther away a galaxy is, the faster it appears to be receding. At modest distances, the expansion is gentle, but at extreme distances, recession speeds exceed the speed of light. This is not a violation of relativity, because nothing is moving through space faster than light. Rather, Space itself is expanding in a way that increases the separation. Yet the effect is the same. There are galaxies so distant that their light can never reach us. Not because the light falters, but because the space between us expands faster than the light can cross it. This creates what cosmologists call the cosmic event horizon, a boundary beyond which events will never be observable from Earth. Objects beyond this horizon fade irreversibly, not into darkness, but into inaccessibility. Their light begins a journey it can never complete. The paradox is captured in a single, quiet truth. The universe contains regions that exist, but for us, will remain permanently beyond the reach of sight or information. If the Milky Way is an island of stars and the local group is an archipelago, then the universe beyond the event horizon is an entire ocean whose distant shores are moving away faster than any message can travel. The lightyear becomes not only a ruler, but a limit, the scale at which the universe gently refuses to reveal all of itself. This boundary was not always present in scientific thought. For centuries, astronomers imagined an infinite, static universe. The paradox of Olber's dark night sky challenged this. For if the universe were infinite and unchanging, the sky would glow brightly at every point, every line of sight ending at a star. Darkness itself became evidence that the cosmos had a beginning, that its structure was shaped by time. Only when expansion was discovered did the darkness fully make sense. Light from most regions has not yet reached us, and some will never reach us at all. The second paradox arises from the nature of cosmic time. When we look deep into the universe, the distances correspond to earlier eras. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was when the universe was young. And when we look at galaxies near the edge of the observable universe, we see them as they existed nearly at the dawn of time. But the deeper one looks, the more the universe mixes distance with history. The farthest galaxies are not the oldest because they have lived longer. They are oldest because their light began traveling toward us when the universe itself was young. This creates a strange layering. The universe we see is arranged not by where objects currently are, but by when their light began its journey. The cosmos is a time-structured image. It is as though the sky is a collage of moments from across more than 13 billion years, all arriving simultaneously. Even stranger, many of the galaxies we observe near the cosmic edge have, by now, moved far beyond the region from which their light could ever reach us again. The image we see is not the galaxy as it exists now, but a fossil imprint of its earliest state, a snapshot permanently cut off from the present. The paradox deepens the farther we look, the younger the universe appears. Yet the galaxies we see at those distances may today be unreachably remote or transformed beyond recognition. The cosmic expansion ensures that what we observe is a forever receding archive. In this sense, the observable universe resembles a sphere not centered on Earth, but centered on the present moment of observation. Every observer, anywhere in the cosmos, would have their own sphere of visibility, shaped by the speed of light and the age of the universe. Each observer occupies a different bubble of knowable existence, bounded not by matter, but by time. A third paradox appears when we consider interstellar life. If the universe is full of stars, many older than the Sun, and if planets are common, which we now know they are, then why do we see no evidence of technologically advanced civilizations? This question, known as the Fermi paradox, is not simply a philosophical tension. It is a tension grounded in distance, time, and the light year. Interstellar distances are unforgiving. Even the nearest star lies 4 light years away, a gulf far too large to cross with any current technology. Communication across thousands of light years would require time frames surpassing the lifespans of civilizations. Light is fast, but not fast enough to sew the galaxy into a single communicative fabric. But distance alone does not explain the silence. The more one understands the age of the galaxy, more than 13 billion years, the more the silence gains new weight. If advanced civilizations had arisen often, their signals might have had millions of years to travel, yet the night sky remains quiet, filled with stars but devoid of messages. Some argue that we may be isolated by sheer cosmic separation, cut off from others by the speed of light and the expansion of space. Others suggest that civilizations may rise and fall before their signals can traverse meaningful distances. Still others propose that the galaxy may be full of life, but that life rarely becomes technological, or rarely chooses to broadcast. In each explanation, the light year plays a central role. It defines the maximum speed of information, the maximum range of influence, the maximum domain of awareness. Distance becomes a filter, screening off interactions that might otherwise have occurred. The silence of the galaxy may not imply emptiness. It may simply reflect the boundary imposed by cosmic scale. The fourth paradox lies in the nature of simultaneity. In everyday experience, events happen in an order that seems absolute. A moment is a moment. A second is universal. But relativity teaches that this is not true. Simultaneity depends on the observer's motion. Two events separated by great distances may occur simultaneously for one observer, but not for another. When distances stretch across thousands or millions of light years, this relativity becomes unavoidable. Imagine two supernovae exploding in different regions of the galaxy. Their light begins traveling through space, but one beam may reach Earth centuries before the other. The explosions may have occurred at the same moment in the star's own frames of reference, but by the time their light reaches us, they belong to different eras. Even more striking by the time we see a star explode. The remnants of the explosion have already expanded for centuries. The present we observe is not the present that exists. This relativity of simultaneity creates a universe with no universal now. Every location experiences its own present, determined by the paths light has taken. Distance fractures time into local realities. A light year is not only a measure of separation, but a measure of temporal disagreement. The farther apart two points are, the less meaningful it becomes to ask what is happening right now at both locations. In the deep universe, now dissolves entirely. The largest structures cannot share a single moment. The cosmic web does not possess a unified present. Every observation becomes a negotiation between distance and time, between the origin of the light and the moment it is received. The fifth paradox is the most dramatic. The limits of visibility create the illusion of a boundary to the universe. When we observe to the edge of the cosmic microwave background, we see a sphere roughly 46 billion light-years in radius, the size of the observable universe. But this sphere is not the size of the universe. It is only the region from which light has had time to reach us. The true universe may be far larger, possibly infinite. The boundary we perceive is not physical, it is temporal. This means that everything we know, everything we can measure, every galaxy ever discovered, exists inside a bubble defined by the travel time of light. Beyond that bubble lies the unobservable, a realm whose existence we infer but cannot confirm. The light year, once a unit of distance, becomes the radius of a horizon. The edge is not a wall, but a consequence of cosmic infancy. We are limited not by tools, but by the age of the universe itself. The last paradox arises from human perception. The more deeply astronomers study the cosmos, the clearer it becomes that our intuitions, shaped by life on a small planet, fail to grasp the shape of reality. Distance does not behave as expected. Time does not behave as expected. Expansion, curvature, and relativity warp concepts once taken for granted. The universe is not designed to be comprehensible to a mind evolved for survival on a single world. And yet, despite this mismatch, despite the vast separation between human scale and cosmic scale, the mind persists in its search for clarity. It builds instruments that pull in faint light from the edges of time. It constructs equations that predict behavior billions of years into the past or future. It creates virtual universes to simulate the growth of structure under gravity. In doing so, it participates in something far greater than observation. It participates in translation, turning cosmic phenomena into human understanding, turning scale into meaning. Every paradox encountered in the deep universe reveals something essential. The light year is not simply a ruler. It is a conceptual threshold. When distances grow large enough, they cease to describe static positions and instead describe dynamic relationships between information, expansion, causality, and perception. The paradoxes arise not because the universe contradicts itself, but because it contradicts the expectations carried from human experience. In the dark between galaxies, the universe teaches that distance is never simple. It stretches, it accelerates, it separates, it obscures. It creates silence where communication cannot cross. It creates horizons where knowledge cannot reach. It creates illusions where time and space blur. Yet, in this vastness, a question lingers beneath the paradoxes. Subtle but persistent. What does it mean to exist inside a reality whose deepest structures can be glimpsed but never fully seen? What does it mean to stand inside a sphere of visibility whose expanding edges carry the imprint of the universe's birth? As the paradoxes settle into awareness, they do not close doors. Instead, they prepare the mind for the next frontier, the exploration of possibilities that arise when the limits of known physics meet the imagination of future science. For all its paradoxes, the universe has never been silent about its potential. The light year, with all its limitations, does not simply restrain the imagination, it challenges it. Every boundary becomes an invitation to rethink what motion, communication, and presence could mean on scales far beyond a single human lifetime. The cosmos may stretch faster than light can chase, but nothing in its immensity forbids us from imagining futures that reinterpret distance itself. Standing at the threshold shaped by paradoxes, humanity begins to ask not only what is, but what might yet become. The first insight that shifts perspective is simple, although nothing outruns light. The universe does not require travel to extend perception. Most of human understanding of the cosmos has come not from motion, but from reception. Telescopes gather photons and turn them into meaning. Observatories transform faint signals into stories of star birth and galaxy formation. In the next century, perception itself may evolve into a form of exploration that rivals travel. The telescopes of the future, freed from the constraints of Earth's gravity and atmosphere, could be placed far beyond the orbit of any planet. Arrays stretched across millions of kilometers by solar sails might combine their signals to create images of distant planets so detailed that the continents, oceans, and cloud systems of alien worlds could be resolved as clearly as satellite views of Earth. This would not be travel in the conventional sense. It would be something else, presence through precision. The light year remains intact, but the future bends its consequences into new shapes. Instead of shortening distance, we learn to lengthen perception. Instead of outrunning light, we learn to listen more deeply to what it brings. Yet even with better perception, humanity's curiosity presses against the urge to close the gap physically. Living worlds may exist in the nearby stellar neighborhood. Worlds with biochemical signatures written into their atmospheres, worlds that are habitable or even inhabited. The distances, though staggering, are not infinite. 4 light years to Proxima Centauri, 11 to Tau Ceti, 39 to TRAPPIST-1. These numbers are insurmountable with chemical rockets, but they are not insurmountable for the imagination, nor for physics. Concepts like nuclear pulse propulsion, fusion drives, and beamed sail spacecraft already exist in theoretical frameworks. Some of them push speeds to 10% of light speed, perhaps 20. At such speeds, Proxima Centauri becomes a 40-year journey, long by human standards, but trivial on cosmic scales. A civilization thinking in centuries, not decades, could begin to view the lightyear not as a wall, but as a frontier. If such missions ever launch, they will redefine the meaning of human presence. The destination will be invisible for most of the journey. Signals sent home will lag behind by years. A crew, if any survives, will live out their lives knowing that Earth remains a distant echo. And yet, this form of separation has always been part of our story. When ancient Polynesian navigators crossed the Pacific, they sailed for horizons they could not see, guided only by stars and waves. When early explorers left Eurasia, they did so without promises of return. The great distances of the universe amplify that impulse, but do not extinguish it. The future may remember interstellar probes as the first gestures of a species beginning to understand its place in a galaxy more immense than imagination can fully grasp. Still, standing beneath these bright possibilities, another quiet truth settles in. Faster travel does not guarantee closer contact. Even with improved propulsion, even with near light speed voyages, the universe remains immense beyond measure. To cross the Milky Way from end to end would require more than 100,000 years even at light speed. The time frames stretch so far beyond human experience that they dissolve the very notion of arrival. If a civilization does someday expand across stellar distances, it will not resemble the exploration stories told in decades or centuries. It will resemble a slow, patient migration, unfolding over millennia, an emergence of presence rather than a conquest of space. This vision carries its own beauty, a species that moves across the galaxy slowly. Over time, does not extend itself through force, but through persistence. It does not impose itself upon the cosmos. It adapts to its rhythm. In such a future, the lightyear becomes not an obstacle, but a cadence. The tempo of a civilization that has learned to live within cosmic time rather than against it. There is another path forward, one that does not require physical travel across vast distances. The manipulation of space-time itself, general relativity allows, in principle, for exotic geometries, wormholes, warp bubbles, shortcuts that reduce enormous distances to traversable ones. Though these remain theoretical, constrained by enormous energy requirements and unresolved physics, they persist in scientific discourse because they reveal something essential. They remind us that the universe's structure is not yet fully known. What seems impossible today may someday be reframed by new knowledge, new discoveries, or new forms of energy we cannot yet imagine. The lightyear feels absolute, but in physics, absolutes sometimes soften under new frameworks. Even if wormholes never materialize, even if warp drives remain abstractions, the contemplation of such ideas expands human imagination. They teach that our current limitations may not be final. They show that the universe is not a closed book, but an open manuscript still being written by the laws we have yet to uncover. Each speculation pushes the mind beyond familiar edges, preparing it to see reality in forms that challenge old intuition. Yet the future is not only shaped by what humans might build, it is also shaped by what the universe is already doing. The cosmic expansion, accelerating under the influence of dark energy, will eventually separate galaxies so thoroughly that communication between galaxy groups will become impossible. In a distant future, hundreds of billions of years from now, the sky will darken as galaxies move beyond each other's event horizons. Civilizations that emerge late in cosmic time may never know the beauty of a star-filled sky beyond their local group. They may assume, quite reasonably, that the universe contains only a handful of galaxies. They may never see the cosmic microwave background. They may never discover the full expansion of the cosmos. Their understanding of reality will be constrained not by ignorance, but by physics itself. This future raises a quiet question. What does it mean to be alive now? In an era when the universe is still visible, what does it mean to have access to the full scale of the cosmos? Humanity occupies a remarkably brief window in cosmic time, a moment when the universe is transparent enough to study, but old enough to have developed structure. Had we evolved billions of years earlier, there would have been no galaxies to observe. Billions of years later, there might be too few within reach to infer the universe's past. Our era is a fleeting clarity in an ever-changing cosmic landscape. From this vantage, the possible futures branching outward appear even more fragile and precious. The tools we build now determine how much of the universe future generations will understand. The equations we discover, the maps we draw, the observations we archive. All will serve as guides long after most of the visible cosmos has slipped behind the curtain of the event horizon. The future may depend less on how far we travel and more on how well we preserve the knowledge that the sky once offered. In contemplating this, another pathway emerges. A future shaped not by expansion outward, but by reflection inward. Technology may advance to the point where energy extraction from black holes becomes feasible, where civilizations build around the accretion disks of supermassive stars, drawing power from the rotation of space-time. Dyson spheres, megastructures that capture the full output of a star, might one day become not symbols of conquest, but adaptations to dwindling cosmic resources. In such futures, humanity's descendants may remain within a small region of space, yet possess an awareness of the universe far beyond what distance would otherwise allow. The lightyear, in that future, would remain a measure of separation, but separation itself would no longer define the limits of understanding. Advanced civilizations might create simulated universes with physical laws modeled on the real one, exploring conditions that cannot be replicated in telescopes. They might reconstruct ancient galaxies from preserved data, turning remnants of the cosmic microwave background into virtual windows on epochs long vanished. In these futures, distance becomes less of a barrier to knowledge and more of an aesthetic, the background shape of a world that has learned to think in scales that dwarf human intuition. And still, beneath all speculation, there lies a thread that ties every possibility together, the human desire to know, across disciplines, from astronomy to physics, from philosophy to engineering. The pursuit of understanding drives imagination forward. The light year, though rigid in definition, bends under this desire. It becomes not only a ruler, but a symbol of the mind's capacity to stretch outward, to encompass distances it cannot physically cross. The future imagined here is not guaranteed. It is an invitation, shaped by curiosity. As the narrative deepens, a subtle tension appears. For all the grand visions of interstellar travel, space-time manipulation, and megastructure engineering, there remains an undeniable truth. The universe may refuse to yield its deepest secrets, regardless of how boldly they are pursued. The cosmic horizon may expand faster than knowledge can reach. Dark energy may accelerate the separation of galaxies to such extremes that information becomes trapped in isolated volumes. The ultimate fate of the universe, whether heat, death, Big Rip, or something yet unknown, may erase all traces of its origin. In such a future, no amount of technology could fully overcome loss. There will always be things that lie beyond observation, beyond inference, beyond recovery. The light year becomes not only a distance we cross or imagine crossing, but a memorial to everything that remains unreachable. And yet, even in the face of unreachable distances, the mind continues to seek meaning. It continues to build models, to ask questions, to contemplate futures that blend physics with hope. Perhaps this is the most profound possibility of all, that the significance of the cosmos does not depend on conquering its distances. Rather, It depends on how deeply a species chooses to understand its limits. Perhaps the future of cosmic exploration is not a story of expanding outward endlessly, but a story of expanding perspective. Learning to see beauty in constraints. Learning to interpret existence through the lens of time rather than space. There is a quiet dignity in this. A species does not need to traverse the galaxy to belong to it. Awareness itself is a form of presence. Understanding itself is a kind of travel, insight, carried across generations, becomes its own cosmos, its own continuity, its own legacy. Human minds cannot cross 100,000 light years, but human knowledge can unfold across epochs, passing through the future like a long, persistent wave of curiosity. In contemplating the possible futures, the narrative circles back to something simple and fundamental. The universe is not obligated to be accessible, its scale is not designed for comprehension, and yet, here we are, measuring it with rulers made of light, imagining technologies that recast distance into design, shaping futures that stretch far beyond the boundaries of our age. The possible futures are not predictions. They are reflections of what becomes imaginable when the light year is no longer seen as a wall, but as a foundation. The dark between galaxies will always remain vast, but in that vastness, there is room for endless possibility. Some futures will be defined by exploration, others by understanding, others by adaptation. All of them, however different, share a common center, the quiet resilience of curiosity. After traveling outward for so long, tracing the paths of ancient photons and walking the long corridors of cosmic time, there comes a moment when the direction reverses. Not because the universe grows smaller, but because its vastness begins to echo inside the observer, the light year. Once a measure of unreachable distance, folds gently into something more intimate, a way of seeing the connection between the outer world and the inner landscape. Every observation of the sky begins as a physical process. Photons enter the eye, strike the retina, trigger electrical impulses. But what happens next is far less mechanical. The mind turns those signals into meaning. It turns starlight into memory, distance into metaphor, cosmic history into personal reflection. The universe is not merely something we look at. It becomes something that shapes the way we think, the way we locate ourselves in time. The atoms in the body carry their own form of cosmic memory. Carbon forged in ancient stars, iron born in supernovae, oxygen released by the first photosynthetic organisms. To return to the self is not to leave the universe behind, but to recognize that consciousness is one of its quiet, improbable expressions. Even the act of wondering about distant galaxies is a continuation of processes that began billions of years before Earth existed. In that sense, thinking is a form of cosmic archaeology. Each thought is an artifact of deep time, rearranged into something fleeting and human. Perspective shifts here. When one contemplates distances measured in light years, ordinary worries become lighter, not trivial but repositioned. They no longer fill the entire field of view. They drift, like small clouds against a wider horizon. The universe does not diminish the self. It reshapes the scale on which meaning is measured. A single decision or disappointment becomes one point within a timeline that stretches far beyond immediate emotion. In that space, clarity often appears. The mind sees its own patterns with more honesty, more gentleness. What the light year ultimately teaches is patience. It teaches that not everything arrives instantly. That understanding requires distance, and that some truths can only be seen when enough time has passed for them to travel the length of one's life. The cosmos is relentless in its scale, but generous in what it reveals about perspective. In learning to interpret the sky, the observer learns, quietly, to interpret themselves. At the end of the journey, the universe does not grow louder. It grows still. The light years fall behind like long shadows, and the vast machinery of galaxies settles into a kind of distant hum. Nothing more needs to be measured. Nothing more needs to be proven. What remains is simply the awareness that you are here, conscious in a universe that does not require consciousness, reflecting on distances that do not require reflection. And somehow, that awareness feels like the most improbable phenomenon of all. All the while, the universe continues as it always has. Stars form and collapse. Galaxies drift farther apart. Light travels with patient precision, carrying the history of everything it touches. Yet, here you are, capable of noticing it, capable of caring about the difference between a kilometer and a light year, capable of imagining futures far beyond the scale of a single lifetime. The cosmos does not ask for this attention, but attention is given anyway, freely, curiously, almost reverently. In this quiet, the boundary between the outer world and the inner world softens. The sky is no longer a distant stage. It becomes a mirror that reveals the structure of thought itself. The way light stretches across time becomes the way memory stretches across experience. The way galaxies drift apart becomes a reminder of how lives diverge and converge. The physics of the cosmos becomes a language for understanding the subtler motions of being human. And then, without effort, the question emerges, the kind that does not seek an answer, only understanding. After everything learned about distance, time, and the strange precision of light, the question turns softly toward the present moment. If the universe is vast beyond comprehension, and if you occupy only a fraction of its history, what will you do with the small interval of light that belongs to you? It is not a challenge, it is an invitation. The cosmos is indifferent, but not hostile, immense, but not inaccessible. It offers its scale not to diminish you, but to give space for your own clarity. Every life, no matter how brief, becomes a point of illumination, a single pulse of awareness in a timeline that stretches billions of years in both directions. You cannot cross a light year on foot, but you can shape meaning inside a moment. You cannot visit distant galaxies, but you can choose how to interpret the light that reaches you. And so the story doesn't end with answers, only with perspective. The universe remains vast. The distances remain immense, and the questions still unfolding. But within that immensity, one quiet truth remains. Existence itself is like light brief, traveling, and always reaching for something beyond. Good night.